Hello, this is Mrs. Nearing, and I'm going to make a video going over Lab 15 calculations, which is the determination of the Keq of this iron thiocyanate system. So this right here, I've highlighted equation number 2 from your lab handout. This is the thing that we're trying to find the K value of. Notice how there are hydrogen ions involved here. We dissolved all our solutions in 0.5 molar nitric acid, and that was to make sure that iron was oxidized the right oxidation number. So there's some other stuff happening there. So made the reaction a little bit more complicated. There's some hydrogen involved in it. Make sure you're looking back at this reaction when you're doing your ice charts and calculating K. So let's move ahead. The first calculation you're asked to do is to determine the concentration of iron thiocyanate. Remember, that's your red stuff. That's the stuff that's making it absorb light in your known solutions. These are the numbered solutions 1, 2, 3, 4. So if you look back at your procedure, you'll find this data table there, which has important information in it about how these solutions 1, 2, 3, and 4 were made. And right above it, you'll see this reaction right here. You've got iron 3 plus and SCN minus ion making FeSCN 2 plus. And what's happening in part 1, notice how we're adding a ton of excess concentrated iron nitrate. So what that does is it makes this normally like two-way reaction. We basically are kind of forcing it to go to completion. So it's behaving as if it's like a one-way reaction here because you're adding a bunch of excess iron. And what that means is that SCN is our limiting reactant. And so we can treat this just like a regular stoichiometry problem that we're familiar with, where we have a volume and a molarity of our limiting reactant. So like for example, in solution 1, we have 3 mils, which is 0.0030 liters, and our molarity is 0.0020. So we can take our molarity times liters to find moles of SCN minus. Okay, so that's step 1, find moles of SCN minus. Step 2, use your mole ratio to find moles of FeSCN. Notice in this case that's easy because it's a 1-to-1 mole ratio. And then that'll give you moles of FeSCN. Then you take your moles of FeSCN and divide it by your liters of FeSCN. And what may that be? Well, look over here at your data table. Your total volume, it looks like, was 200 milliliters. So you take your moles and divide it by 0.200 liters. Don't forget to convert milliliters to liters. And that will give you your molarity for standard 1. And you do the same thing for your various solutions. So you got 4 solutions here. Okay, so next step, your graph. So your graph should look a little bit like this. You should have molarity, and don't forget your molarities were in units of like 10 to the negative 5th probably, so those are very small numbers. So this is molarity of FeSCN. And where did these numbers come from? Well, they're coming from these calculations you did right here. Okay, so these calculations are going to be in pretty small numbers, like something times 10 to the negative 5th molar. One of them is going to be times 10 to the negative 4th. So your solutions are pretty dilute. And that's going to be your x-axis is concentration of FeSCN. Your y-axis is going to be absorbance. Absorbance is a unitless number, so no units on your y-axis. And you should have a graph, so you have some data points here, and then you're going to make this, linear line there. Okay, so it should be nice and linear. It should go through the origin because it's 0 concentration. That's your pure water. That's your blank. It has 0 absorbance. So your graph should look a little bit like this. When you find the slope of this line, you will find that the slope of this line is somewhere between maybe like 4,000 to 7,000. I'm going to put out a big range there because it's going to vary based on your spectrophotometer you used and what you had the wavelength set at precisely. And that's the reason why we do this whole calibration step, is to figure out what this number is. So every group's going to get a slightly different slope based on your calibration for your equipment. Okay, then we get to the next page of calculations. In order to do an ice chart, you need to know some initial concentrations and your final concentration, equilibrium concentrations. So first we have to find your initial thiocyanate concentration for solutions A through D. So again, look back at your procedure for this data table that reminds you how you made these solutions. And at first glance, this might seem easy. You might say, well, isn't the molarity given to me? Whoops, isn't it given to me right here? Why do I need to do a calculation? I thought it was 0.0020. But remember, when you made these solutions, you had them in like a test tube, and like, let's look at solution A, you added 2 mils of SCN, and you added 5 mils of iron, and you added 3 mils of HNO3, and we want to know what is the concentration here in that mixture, okay? So notice we added a bunch of stuff together, so now it's diluted. So it's not 0.002 anymore, it's going to be something less than that. So if this is a dilution problem. When you have a dilution problem, you can use M1V1 equals M2V2. So like for solution A, you would say, well, initially I have 2 mils of my KSCN solution, and it had a molarity of 0.0020 molar. Afterwards, when I mixed all this stuff together, it looks like my volume is now 10 mils. What's the molarity? I don't know. That's what I'm trying to find. Okay, so you're going to be solving for your diluted molarity. Same thing is happening in problem 2. In problem 2, you will notice that each of your test solution received the same volume of iron, so you only have to do this calculation once. It's going to be the same for every test solution. Okay, so it'll be the same for all 4. No, you don't have to show it 4 times. That'd be silly. If you did show it all 4 times, that's fine too. Okay, so that's that one. Then looking at 3, determine the equilibrium concentration of FeSCN using your calibration curve. So here's where you use that graph that you made. So remember you had a graph that looks like this. Your y-axis was absorbance, your x-axis is molarity, and you have this slope, y equals mx. And the slope of the line ended up being somewhere the 4,000 to 7,000 range. For the purpose of this, let's call it 5,000. Okay, so you have a slope of your line, goes to the origin, so there's no y-intercept. If you think about what y and x stand for, y is absorbance, 5,000 is your slope, something like that. This will vary, so please don't just use 5,000, use whatever your slope was. And then x is your molarity. So to find molarity, we can rearrange this. Molarity is absorbance divided by your slope. Okay. And the units should work out because your slope of your line actually is going to have units of molarity to the -1. And so you'll end up with a unitless number divided by the inverse of molarity, which gives you molarity, if you are good and paying attention to units there. So taking a look at problem 4, you want to make an ice chart. So now that you've found your initial concentrations and an equilibrium value, you want to make an ice chart. So remember, you're using equation 2, so you're going to draw out an ice chart, ICE, and then you're going to look back through your calculations and stuff and say, what do I know here? Okay, so I know an initial concentration of iron because we put in iron, okay, and we found that. Let's look back here. We found this in problem number 2. Okay, so problem number 2 is where you found the initial concentration of iron. So I'm just going to say this value comes from number 2. Okay, you also know the initial concentration of HSCN. Let's flip back to that. You found that in problem number 1. And that might seem confusing. You might be saying, well, but I found KSCN, and that's not the same thing. It turns out it is the same thing, because what happens, KSCN, you put it in water, it's going to make K plus SCN minus. Why? Because your alkali metal compounds are soluble. So it's going to dissociate. And then what's going to happen is we put it in a strong acid, so there's these H plus ions floating around, and it ends up making HSCN. So basically, your KSCN is the same thing as your SCN, which is the same thing as your HSCN. So the takeaway is that what value goes in here is the value you calculated in number 1, okay, your concentration of SSCN. Initially, we had no product, okay, and then your H plus ion concentration is 0.5 molar. Why? Because if you take a look back at our ingredients, everything was dissolved in 0.5 molar nitric acid. So H plus concentration is 0.5 molar. All right, what else do we know? We took this absorbance. Like, what was the point of that? Well, the absorbance gave us our concentration of our colored species, which is the FeSCN minus. So in problem number 3, we found the molarity of the FeSCN 2+, that's the red stuff, okay, and that'll give us our concentration of that at equilibrium. So again, going back to problem 4, what should go in this box is the answer from calculation number 3. So you're going to know initial values for iron, HSCN, and H+, and you're going to know your equilibrium value for FeSCN. If it starts out at 0, like, let's make up a number. Let's call this, I don't know, 0.003. If it starts out 0, ends up at 0.003, I know what the change is. And remember, if you know one of the changes, you can figure out all the other changes based on the mole ratios. This one's nice because it's all 1-to-1 mole ratios, so that makes that part easy. And since you know these numbers initially, you can just add the change or subtract as needed to find the equilibrium value. So it's just going to be the same as what we've done. Initial plus change will give you equilibrium value. Remember, the sign on one side of the arrow is going to be opposite than the other side of the arrow. So since my sign over here is positive, that means my sign on the change on this side is going to be negative. Okay, so you should be able to fill in your ice chart. And then once you've filled in your ice chart, you're going to go and plug your values from your ice chart into your Kc expression. So just the big thing with this one, your Kc expression, is don't forget about the H+. So it's FeSCN 2+, and then you've got this 0.5 molar H+ hanging around, and then you've got divided by Fe and HSCN, and there's no coefficients. You don't have to worry about squaring or cubing anything, so that's nice. So you should plug some numbers in. You should get an answer that's, close to 50. If you're getting anywhere from 40 to 90 is great. If you're getting somewhere in the hundreds, maybe maybe double check to make sure you didn't forget to add in the H+, or just check your calculation somewhere. But I would say, yeah, 40 to 90 range is definitely good, and I believe that is it. So email me if you have any other questions. Thanks for bearing with me as I do this new program here.